All right, good morning, everybody. Let's get this thing started. Just a few housekeeping. So the idea for this morning's session is to present for 5 minutes each. All attendees will get 5 minutes of time. You are welcome to use PowerPoint if you have some slides, or you could just talk freely. You should try to wrap everything up in 5 minutes, and Stefan is here going to really enforce that 5-minute rule. And if you leave some time for questions, we'll go with the question and answer. I'll kick it off, and we'll serially go through the list. So Nenad is going to be next, and then Hazen, and so on. I'll go first, and then we can serially go through the list. Okay, so it was really exciting getting a chance to meet with.
So for everybody, also from the online folks, for those who are here, so after 3 minutes, I will just give you a 3-minute warning that you know it's 3 minutes, so that you can kind of pace yourself if you want to allow for questions or if you want to fill out the 5 minutes just talking. So it's up to everybody of you for themselves, okay? And after 5 minutes, I will stand up and throw this thing at you, okay?
And hopefully you catch. So it was really exciting meeting you all yesterday. I'm Raghav Chetri, for those of you I didn't get a chance to formally meet. I'm a member of the Keller Lab. I'm a research scientist here. And I've been a member of the lab since I first started as a postdoc here. And when I look back, it's not that long ago, but when I look back, it's been a very fun-filled journey. A lot of adventure, a lot of chance to work on good science and so on, but also peppered with teaching moments, failures and so on, right? And those, I think, are really crucial in giving us a pause to think about what we could do better. And one such example is the topic of this workshop today, which is the control software for microscopy. I recall walking into the Keller Lab, like a bright-eyed postdoc, and then going into a scope room, and I was just awestruck and amazed by the sight I saw. It was a very experienced developer controlling the scope remotely, right? So he's debugging everything, and that was something that I was not used to in my incarnation as a non-Janelia scientist. But that's the way things were done at Janelia, and the choice was made to use Labview, which, as most of you know, is a very powerful platform, as a closed platform, which has an integrated suite of integrated hardware and software solutions, and it's a graphical user interface. So you are basically connecting wires as if you're wiring electronics, and for loops, you're basically like putting things inside a box. So for an electrical engineer that want to prototype, it's very easy and convenient. But at the same time, it does come with a lot of baggage in that over time, your code gets very massive, and the code base becomes like very much a spaghetti, right? And it doesn't integrate very nicely with GitHub, so there's no like version control and so on. So in the end, the situation we are in is we have these experienced Labview developers that help us get to the final goal we need to get. But as a life scientist or as a scientist working with these scopes, you either have to get to their level of expertise to actually contribute with the control software, or you're really relying on them, right? And as a closed system, again, it's a very powerful system. It's a closed system, and as closed systems go, it's very hard to deploy to another lab, and transfer of knowledge becomes really challenging. It's not without challenges, and we've seen that in a few instances already. And that brings back to the workshop. Okay, so that model of a closed system that probably works great for, say, like an engineering firm that has a closed model, that may not be the model that works great for open science, for the life scientists among us, for the microscopists among us. So what I really hope is that we have a software solution that we can kind of drive as a community that is developed out in the open, and then that actually allows people at all levels, amateurs, semi-experts, and experts, to kind of contribute in their own ways. So hopefully there's like a low-level platform where the experts are driving all the cool development, and then semi-experts have an interface to high-level language that they can do things to their microscope and talk to microscopes easily, and it's not something that is frightening to an amateur to pick up and learn from. And as I was thinking about what are the things we would need in this next generation control software, the things that we value in the scopes that we build are a few things, right? So we need very good timing control, and I think Labview does a good job in those regards. So we need timing that are very precise in the millisecond range, and you want to make sure, and latency that is microseconds. The other thing is synchronization across multiple data acquisition boards. You want to make sure the synchronization stays throughout, and we have a couple speakers here that are going to talk about data acquisition stuff and hardware. We also want to make sure that it scales to distributed system where we have client and server models, and I think this is where Labview does very well. But again, stepping back from all these technicalities, we want to make sure that this is driven by life scientists and experts that can drive the project, but is also accessible to all the rest of us. And more importantly, these experts need to be supported by the science gods, right? Institutes that have the fortitude to support that kind of effort sustained. And I really hope we can come up with like a consolidated effort and a list of things we want in the community so that we can present that to the science gods that I was mentioning. Thank you. I look forward to listening to more ideas.
Unfortunately, there's no time for questions.
So you're next.
I'm next. Do I come?
Yeah.
Okay, so I'm Nenad Amadai, and as Nico introduced me yesterday, I worked with him in the early days of Micromanager, and right now I have a small consulting company, and we build imaging solutions for usually smaller biotechs, academic institutions, and also some bigger names in the industry occasionally. I have a team of about 4 developers. Sometimes that number varies, but depending on the project. But that's pretty much what I'm doing right now. And lots of our work is based on Micromanager, and more or less sometimes. So we built large automation systems with multiple microscopes, with high content, high throughput capabilities, and also client-server solutions where you control multiple scopes from a single point. In fact, make a microscope a network appliance. Also integrate with web services so that you can have authentication, access control, and whatever. And also we build embedded systems, so if you need to put a Micromanager backend into a microscope and turn it into a network appliance, that's pretty much our specialty. So what I find Micromanager platform absolutely something that I can't, there is absolutely no alternative for projects like that. There is nothing else I could use. Regardless of how much money you want to spend on buying, you're definitely not going to use Zeiss or Nikon or whatever software there is, because that's impossible to do. So I'm really interested in seeing Micromanager continue, and I don't really care whether it's completely rewritten and reincarnated from scratch, or it's incrementally improved. What I would like to see is some kind of a core group or a core, I hate to use the word committee, that sounds horrible, but some kind of stewardship, very clear direction from a certain group or a person or institution, because I think that's really important for the future. Also, I think the things that I believe are most important to address is interfaces between components in Micromanager. So look at it as a platform, not as a monolithic Photoshop for microscopes, but rather as a platform that you can build many, many different applications very easily. That's just my viewpoint, and this is the aspect from what I'm really observing this. So I would like to see interfaces. I would like to see some kind of stewardship emerge, somehow from this meeting, and definitely some work in documenting and making it really, really easy to use for people. That's it.
Okay, we have time for one question. Mm-hmm. Or we can also move on and discuss later.
Yeah, let's move on. Yeah.
Okay. Andreas Boden, you're next. Oh, sorry, Hazenberg. Sorry. Also, the online attendees, would be nice if you would switch on your videos so we can actually see you as you can see us, if you can hear us. Oh, thanks. That makes it a bit more personal. Like, hi, everyone.
Okay, so can you hear me? All right, so my name is Hayes Babcock, and I thought it was, so maybe I'm not speaking properly into the.
I believe it's working.
I'll hold it up.
You can just use this if you feel more comfortable.
For this room, I think we'll be fine, but for the online people.
So okay. So again, sorry to go. So my name is Hayes Babcock, and I currently work on the software package called Storm Control. So this is something that I was part of developing in HHMI Janelia lab, and that I am still working on now that I have a different position. And so many of you are probably not familiar with it, but it's sort of a Python package, and sorry. It's primarily in Python, and then it has a little bit of C code for doing things like scaling images. And then I use PyQt for a GUI, and if you're interested, it's available on GitHub. And it was originally it's HHMI Janelia lab was all about storm, acquiring storm data, and now it's more going towards Murfish and multiple cameras. And so what has been important for this project, and sort of these maybe be the likes or the goals of the project. One was that, especially for Murfish, it's really about how fast you can take the pictures. So you need to take a picture, move, take a picture, take a picture. And so we were trying to really have emphasize the parallel processing so that it could do several things at once. Stage could move while the camera was being prepared to take the next picture. And so that was the one thing. The second thing that we've been really working on is we have a couple of different microscopes. So it's a single lab, but every microscope has its own quirks. People have one slightly different camera, different stage, and so forth. So like any sort of software thing, it had to be able to handle all that. And so in this case, we decided to use an XML file that would describe the hardware so that you could, rewrite the XML file. It could control a different microscope without having to reprogram the software itself. And then the third thing, and this is more like a personal philosophy thing, but I see some things like NIS elements, and I see 10,000 different buttons on the interface, and whoa. I didn't think I could handle that. And so we really try to keep it very simple, so it only has a few buttons, and then everything is basically in some config files. So the idea is okay, you want to do storm, so here's some people in the lab develop these files. This is okay, this is what you use. You use these 2 or 3 files to do storm imaging. And so this makes it easier. You can load these config files, and you switch between them to do one storm movie and a conventional picture. But it's all hidden in those files, so that the user doesn't have to adjust the preamp gain for this camera. And then, so that's kind of the way it works now. Is sort of what we build it towards. Of course, it has its flaws, and so because of the parallel aspect of it, when it crashes, it can be very hard to figure out. Okay, what was the sequence that led to that crash? Because you just get a sort of backtrace, and it's got this race conditions and so forth, and so you have that kind of issue. Second thing is that because it's sort of been an organic development over quite a while now, probably 10 or 15 years, there's not sort of uniformly written. Just different conventions were adopted at different times, and some of the older code hasn't, made it to new convention. And then I think the biggest problem that it has, and is that it really, maybe it's just intrinsic to this, but it's hard to test on all the hardware, and it doesn't have any automated testing to test on the stage, this microscope. And so you'll make some change, and then you realize that just broke somebody else's setup. And then this can actually happen like again 6 months later because you forgot why I made that change. And then if you had the test, then it does say you just broke it again, but you don't know until they complain and say, hey, this just ruined the setup again. So why don't you fix that? And so that's an important thing I think that the software needs to think about is okay, testing I think is very important, and that's my thing. So that's it.
Thanks.
Okay, my name is Andreas Boden. I come from Ilaria Testa's lab in Stockholm. In our lab, we are kind of divided into two slight sections. It's like the method development part and the application part. And we have our lab within or just beside a more facility service. So us who belong to the method development part, we work on our custom-built microscopes, and then the application people are sometimes using our custom systems, but also a lot of times use the commercial systems in the facility. And in our lab, since I started since the beginning, we've been building our own control software, kind of de novo, as you would call it. And so maybe I'm one of the few people here. I've never used Micromanager. So I think the benefit, or actually the reason we started starting building our own from the beginning was that no one in our lab had a previous experience with Micromanager, and we had a few people coming from a previous lab where they had their own software. So in the beginning, we kind of modified that version to work with our scopes. But over the years, I think by now we've probably rewritten almost every part of it. And of course, the big benefit, I would say, from my point of view, is that the flexibility to do whatever we want with it. For me personally, it's also been very educational to learn. I come from an engineering education, but not really a software development person. So it's been very educational to learn a lot from it, and it also kind of brings you closer to the system you're working with, I think. It also allows for very easy addition of custom tools. We do a lot of our scopes are quite alignment sensitive, so we often write custom alignment tools to help out with these processes, and that becomes quite easy if you have full control of the whole code. But of course, the major drawback, as I think most people who've done these kinds of projects experience, is that it's very time consuming. And I think also it's a very hard balance between writing code that just works for the specific purpose of the day or the week or whatever, and then versus writing something that's really robust and well-functioning over a longer time. And every time I feel if I need to implement something or change something, I'm always kind of torn between the do it fast and make it work so that we can go on with the experiments, or really think hard and deep, what's the best way to implement this? And the same way when you have bugs or problems, it's when you do I just do a quick fix so that we can keep going, or do I really find the source of the problem and build from up? Our ambition was also to have kind of the same software on all our scopes, but then also, as mentioned before, all the scopes are slightly different, and you end up with very different versions of the same software anyway. Yeah, and then of course, documentation is a bit of a problem because it's also very time consuming, but it's the same kind of balance between how much time you spend documenting and making your code really neat and versus doing it quick. Yeah.
Just to clarify,
Yeah, sorry, yeah, we write everything in Python. Yeah.
Python.
Yep.
Thanks, bro.
Okay, great. So my name's Peter Brown. I'm in Doug Shepard's lab at ASU. And so there, my experience is we're working to build a custom microscope that's going to be capable of doing several different modalities. So most recently, I've been working towards a multicolor SIM setup based around a digital mirror device. And I'd say one of the things we're interested in the setup is having nice hardware-controlled timing, things like this, being able to trigger many instruments simultaneously, particularly because we're maybe interested in adding some more tomographic kind of modalities where you would take, tens of pictures that you'd combine into a single image. And so everything that I've done so far has mostly been in Micromanager, although we have a digital mirror device, DMD, at the center of this, and this we're controlling separately. So there's some challenge there, I think, for me to kind of get everything running together. Right, so obviously I think the things I like about Micromanager are probably similar to the reasons other people use it. It's well designed and has a number of drivers, so I don't have to obviously write these things for the different devices, which is great. And the integration with ImageJ, I of course appreciate for sort of debugging things in real time and trying to get things to work well. But I think that it's been a little bit of a challenge to do these hardware sort of intensive experiments because, so I sort of maybe have a very naive perspective on this. I'm coming from a different field. I've been working with Micromanager for 3 months, but it seems very camera-centric. Everything you're doing sort of based around the camera, whereas so I come from the atomic physics world and the cold atom community, and there you're really running a whole experiment with a National Instruments chassis, something like this. So you're doing a lot of more sort of complicated experiments. And so my impression so far is that's something that's harder to do with Micromanager. So I guess, things that I would be interested to see, and I don't know if there's community support for these things, but my perspective is more support for these kind of complicated experiments, and also more support for scripting with languages like Python, which is something that I do all my data analysis in, so that's something I'm more familiar with compared with scripting with Bean Shell and things like this. Let's see. Right, so yeah, I'd say from my perspective, sort of coming at this, learning it in the past few months, I'd love to see more ability to handle these complicated experiments, more integration with other scripting languages. And some of these features, as I say, I sort of have a naive perspective, so some of these features may be there to an extent that I haven't explored, but if they are, some kind of more documentation or examples for how to do these kind of things would be really valuable for me. So that's that's my perspective.
Hello, I'm Ahmet Can. I'm working with Loic Rea in Chan Zuckerberg BioHub, San Francisco, as a software engineer. So I don't have a huge microscopy background or any sort of deep academic experience, but I think this is a great opportunity for me to know and understand what are the struggles you guys are facing day to day, because we are also building microscopes, and for sure we want to make we want to have fun while controlling them, and we want easy stuff. We don't want any big challenges, and by its nature, microscopy control seems to be a quite sophisticated problem, as you guys all know, because of the synchronization of the things, lack of feedback support from possible devices that you guys are using. So that's why, for me, my motivation in this meeting is mostly try to talk with each of you and understand better what are the big problems for you, what are the most cumbersome things you guys facing in terms of controlling those devices, and so that together I believe we can come up with a either keep contributing to Micromanager or come up with anything else that is open source, that supports open science, and in the end of the day helps everybody at some percentage. Yeah, this is my motivation for this meeting. Thank you.
Hello, I'm Yan, and I'm a graduate student from Thomas Lab in Columbia University, and my job in the lab is mainly data analysis of the images and also some software design for our image systems. So in our lab, we have several different kinds of custom-built light sheet systems, and the two most robust systems are using the high resolution imaging based on the large clear tissue samples. And these systems are based on the dedicatedly built Labview programs, and they are also matched with corresponding National Instruments hardwares. And the good thing is they are really robust because they are written by some pretty cool guy very long before I come to the lab. And the bad thing is, currently no one can understand their code, so the whole program cannot be changed. We just use it every time, and if we want to build a new system, we can use them again. So currently, what I'm trying to do, I'm also trying to build a new microscope system, which is a tiny light sheet microscope system. We're trying to minimize the optical parts and make it smaller to fit in the incubator for 3D cell culture imaging. And what we're trying to use, instead of using a whole computer to control this small light sheet system, we are trying to use maybe the NVIDIA Nano board, which is something like a Raspberry Pi to control that. So this is a quite big difference with our previous large system. So we can only build a de novo software based on Python, and it's totally built from scratch. And the problem, of course, is that we have bugs, and also because if it's not very big bugs, we just live along with it because it's enough to get the data. And also one thing is that such code is very hard to synchronize and hard to control that. It's not stable, and also by adding different features, such code will get intermingled with each other because it's not well separated. So as some personal experience, I think we really need a tool which have very clear blocks, separate each part altogether, and also it's very easy, it's very plastic because we have all different customer needs. So yeah, so we want this code to be easy to implement and to use for different customer needs. And we also want that if we can have a very clear guide to show amateurs how to change or how to add some personal extensions, that will be great. Yeah. That's it.
Kevin?
All right, so my name's Kevin Dean, and we use basically anything we can get our hands on. Like, we're desperate. We'll pull code off of GitHub, which we've done. We've messed with Java, Micromanager, Python. We've done stuff in Labview, MATLAB, but really what it comes down to is we keep coming back to Labview. And the main reason why is because we've developed a very strong addiction with Coleman Technologies, which is the firm that does all our software programming for us. And like Raghav, it really just comes down to the fact that we really need good, high precision timing. We need to be able to save data fast. We need, proper metadata. And, we're just not academically rewarded in our environment for developing code. So we're there to really, make papers from the optical technology that we develop, and to really try to make that available to the biology community at UT Southwestern. And so the faster we can do that, the better. And really setting aside a grad student for 6 months or a year writing code is not something that our department chair is going to want to support. So that's really what it comes down to now. I think Labview is a massive pain. Our software has gone to be so complex and spaghetti-like that it's, only one person in the world that I know of can go in and figure out what's going on, and that's the person we pay $200 an hour. So that's not exactly a great solution. It's also just a giant house of cards. We go in, we say, can you make one fix here? And then a bug shows up in what seems to be a completely unrelated area of the software. Again, version control is a pain. And another big challenge is that this software was originally developed in Eric Betzig's lab, and we received a version of it 7 years ago, and it hardly resembles the original software, but it's still subject to an MTA with Howard Hughes Medical Institute. So we can't actually say, hey, you want to build this system, here's the software that can run it, because we can actually get it operating pretty much anywhere. But now we have a third party that we have to get an MTA from. So that's also just legally frustrating. So I think this is a key thing. We all talk about open science and the ability to help one another build optical components and push biology with advanced imaging. But if you don't have a software to run it, it's just a pile of glass and piezos and wires. So I really support the mission of this. So that's about it.
Is it connected?
No. Well, not much we can do at this point, I guess. No.
That's my view from my back garden.
We just started again, wasn't it? I'll just show it like this.
Hey, we've got it. So good morning, ladies and gentlemen. I'd like to echo the sentiments of previous speaker, Kevin. So we moved from Labview some years ago. We were using Labview, C++, and MATLAB. We particularly work in my group on fluorescence lifetime imaging. We have a widely used program called FlimFit for complex analysis. And we also wanted to develop high throughput fluorescence lifetime imaging for FlimFret assays. And we built a hardware platform on Micromanager, and we switched to Micromanager for all the reasons Kevin's just said about Labview, the code getting really labyrinthine and getting killed by updates. And since then, we've also been asked to work. Whatever, this isn't working. We've also been asked to work on single molecule microscopy, so we're building a high throughput storm platform. And having done 2 high throughput platforms, and Sunil Kumar at the back is developing a generic, if you like, micromanager-based high content analysis platform, acquiring images, moving it to Y stages for multi-well plates, etc. And since then, we've also been particularly working on trying to develop open hardware. And I would show you a beautiful image of what we call Open Frame, which is a microscope frame that can be built for a couple of $1,000s, on which you can build Storm or FLIM or pretty much anything else you want to do. It's open source. We've already made the CAD files widely available, and if you go to www.openscopes.com, you'll be able to see our open source software and the CAD files for the open microscope frame. Sorry, the PowerPoint hasn't worked.
Thanks a lot. Or do you want to say?
Do you have a few more?
Okay, questions. Oh. If I have got some time, then I'd just like to quickly say, in Micromanager, we have a few issues. One issue is we're building an autofocus for our high content platforms, and so that's camera based, and so we'd like the ability for having a camera doing something other than looking at the sample. So the multi-dimensional image acquisition is really based around cameras looking at the sample, and so we would like a bit more sophistication there. When we're doing Storm, our file sizes, because we have very large fields of view, can be up to 50, 70 gigabytes, and so we want to be able to handle such large data files. And with our open hardware, we're particularly keen on small companies selling instrumentation using Micromanager as the software and selling the hardware plugins for the open frame, which I can show you on my computer if you want to come and see me. And basically, there are companies that would only do that if they could use their own software with plugins to protect it. And so we spoke to a company last month, and they said, we tried to work with Micromanager, but we're too worried that people could steal our software. And then finally, on the image analysis side, we're very keen, of course, to carry on working with ImageJ, but we generally find when we're rendering 3D images from our optical projection tomography systems, for example, we very often use IC because it can do things better or faster than ImageJ. And so addressing the 3D visualization, I think, is important. And the final challenge is if you're doing 3D imaging, multi-well plate imaging, light sheet microscopy, and so on, you have now huge data volumes, and there are interesting technologies or approaches coming around where people are compressing the data in a minimally lossless way before it's saved. So I'm aware of at least one commercial solution, and I think they're open source solutions, and I think this is a really good idea. In the UK, we're obliged to save our data for 10 years, and if we're collecting a terabyte a day, we can't possibly afford that.
Thanks a lot. Okay, Adam, now we have the first. Online participation.
Yes, can you guys all hear me?
All good.
Okay, great. So I'm Adam. I work with Jonathan Liu at the University of Washington, and we build light sheet microscopes specifically for clinical applications. And I should mention that we're a bunch of mechanical engineers coming into microscopy with very little software expertise. So the precedent in the lab before I joined, and also from my background, was to use Labview. And this worked great for the first few years that we were just starting to build these microscopes. But as everyone else has mentioned, the downsides of Labview were that only one person could read their own code. It wasn't easily shared with other students or postdocs within the lab. And also the code would always crash, difficult to update. And so I think maybe 6 to 12 months ago, I saw, it might have been Nikita actually, someone was talking about making the switch to Python to control their light sheet microscope, and I thought that would be a great idea to try and implement in our lab as well. And so using different things on GitHub, I was able to cobble together something which works. I would say the biggest advantage on our end, the last speaker kind of touched upon it, was the data sizes that we deal with. Sometimes we're generating 20, 30 terabytes of raw data per day, and doing it through Labview was unideal because the flexibility in terms of what format we save the data in was a huge issue. So we would save the raw data in one form, and then we'd have to read it back into RAM and convert it to the form that we actually wanted after imaging, which was highly inefficient. And so now with Python, we can stream the data directly from the camera, and for us, save it directly as a, for example, HDF5 file with the compression that the last speaker mentioned, so that we can just immediately do post-processing. So that's been huge for us, and I think having the flexibility to control the data inputs and outputs is really crucial for us, at least. But the one challenge with Python is that because none of us have deep software expertise, we're able to code something which works for exactly what we need, but we've lost the GUI. None of us have the time or expertise to build a GUI, which is working at the moment, but our end application is to work with clinicians and have clinicians controlling the microscopes. And so down the road, that could be a huge issue for us. And so working with something like Micromanager is something we're interested in exploring, but also understanding whether it can meet our needs based on what I just mentioned. And so I think we could benefit a lot from learning about the topics at this meeting.
Thanks a lot. Maybe it's there.
Yeah. Hi, I'm John Heddleston. I'm part of the Advanced Imaging Center here at Janelia, and you'll see a lot of our team also there along the back wall, so there's a number of us here today. In the AIC, we sit at a little bit of a unique position. So we interface from the microscope developers here at Janelia, as well as the end users that come from around the world to use the scopes at the center. And so while we aren't necessarily involved in the de novo creation of microscope control software, we are heavily involved in the use, maintenance, upkeep, bug squashing side of things, as well as on the other side, how the data comes out, what the format is, how usable is it, how is the metadata transmitted, how do we get the cell biologist at the benchtop who doesn't really know much about software or microscopy, how do we get them comfortable with what comes out the other side and they can actually do something with it and get data, quantitative information out of it. So a lot of our instruments that we use, well, they all run Labview in some form or fashion, and as other folks have mentioned already, the biggest problem we have with Labview is that because we require high precision timing for the stages and the cameras and the shutters, it does become a bit of a spaghetti code, and we're very reliant on either Dan Milkey or Coleman Technologies, that if something majorly crashes and goes wrong, we're a bit hamstrung on being able to fix things. So I don't necessarily think that Labview in and of itself is necessarily the problem, but it's really just the ability to have a platform that is accessible to a lot of people so that you're not tied to just one developer or one code writer. The one thing I will say for Labview that is crucial and that we have found the hard way several times is that a lot of the other hardware companies that we rely on, PI or our National Instruments or what have you, they like to sunset a lot of hardware, a lot of controllers, at will. And having buy-in from these companies to support whatever this control software is to make sure the drivers are updated, that you can easily get working software from them to whatever your platform is critical. Because even with Labview, we've run into problems where National Instruments decides they don't want to run a controller anymore, and now you have no way to run the hardware that you have, right? And especially, and I think Elizabeth had mentioned this yesterday, this is an evolving landscape. And so while your NI controller software might be great for today, in 2 or 3 years, either it's different or it's a different company. And if the control platform that you're sitting on is too heavily tied down to one manufacturer or relies on just one old driver, it's gonna cause a lot of problems. So I think for the meeting, I hope that myself and the rest of the team that's here, we really hope to get out of this not just control software, but really some thoughts from microscope developers and users or operators really, how do we create platforms that are usable at both ends of the expertise spectrum, both the people that are making it, but then the people that do have to use it, because if they're not interested and don't want to use what we're producing, then it's all kind of for naught anyway. So thanks.
to attach here? Is it?
See if this works. Oh, come on. Don't start the clock. Okay, so I brought Richard with me, and I think that means we should get 10 minutes. Okay, so I'm Elizabeth, this is Richard, he's a grad student in my lab. So as you know, we developed scape microscopy, which is a method for very high-speed three-dimensional imaging. We've been slogging around for the last sort of 6 years trying to get people to use it, to try things, to come to our lab, bringing the systems to other places to try to sort of get people to start using this. And so over the last few years, we've been really working hard to get Scape into the hands of people who really need it. Our goal is to be able to get someone who just wants to use this system to be able to get it set up in their lab and start using it. So we fully documented how to build Scape. We have a whole bunch of designs. We've got a bunch of local collaborators. We've built 19 systems to date. We're helping a lot more groups currently get started. We've been bringing Scape to courses, and we've been hosting people in our lab. And Lali in my lab has been really the driving force behind all of this. She's basically our project manager. And the process that we go through is we do a lot of work initially with people to really get them to understand what Scape can do, to check that what they want to do is going to be compatible, which means them sending us samples or coming to try it. We do an MTA because we want to be able to really just share all of this information, but it's a very simple thing just to sort of set things up. And then our packet includes a full parts list, complete construction instructions, including how to build the computer, how to do all the alignment, and we provide them with all of the software that they need, from instrument control to data loading and basic analysis and viewing, and then we help them online, which is again Lali's magical skill. And a lot of this has actually been funded by the BRAIN Initiative. We're in a second round of funding now that includes a big aspect of dissemination. And of course, we've also licensed this to Leica, and that's a whole other thing. So this is us taking the system in a suitcase to Dresden a couple of years ago. This is us. We take it every year to Cold Spring Harbor. And so this is my personal history. In 1997, I did my undergraduate thesis using Labview when it didn't even have an undo button. It was version 1.0. And I said I was never, ever going to do that again. So 2003, when we built our first 2-photon, we made spam image after scan image, which back then was written in MATLAB. And MATLAB's actually got this incredible ability to have a GUI, to have all this beautiful linear code that isn't written like spaghetti. It has data acquisition, National Instruments integration. So I've been a huge fan of it. When we came to starting to try to use cameras, we found MATLAB sucked doing the actual image acquisition. You had to do all of this stuff with ring buffers and memory that was just never going to be fast enough for what we wanted to do. So that we ended up writing in CVI lab windows, which then became that block of code that nobody in the lab dared to edit. So when it came to Scape, we had to make a decision. So the hard part for us is we just want to read the camera as fast as possible. We just want to stream it to disk, and we want to blame someone else if that doesn't work. But the really easy part, and part of why we developed this system and why we love it so much, is it is really, really simplistic. You just move a galvan when you grab the images. There are no stages and piezos, and that is why it can be fast, and that is why we like it. And so what we ended up doing was actually taking the standard software from the camera, which is the Andor camera, which is the Solist software, which now has all sorts of beautiful functionality that tells you with these little graphs whether you have unrealistic expectations about what you can stream to disk, you can preview, you can pick your ROIs, you can do anything you want there. And then we have a little bit MATLAB front end that basically just controls everything. So it writes the config files for the camera, automatically loads them into the camera software. So when you hit go, everything happens seamlessly. We have preview modes. We have different ways in which we can do stuff. And this is all written in MATLAB. I know MATLAB sounds scary in the world of Python, but frankly, everyone in my lab has been taught how to use MATLAB. We've known how to use it for years. It's really not challenging for people to edit the code. Richard started in my lab. Also, Creeper in my lab actually has been really the go-to person on all of sort of maintaining this. And I will say one thing, noting the genders in this room, I maybe could say that women aren't too bad at kind of like making things usable. there's a sort of perspective there. I had a guy in my lab who really wasn't getting it, and I said, Creeper, can you just go and make this usable? And I think there's a value there. But so Richard also came along, and he wanted to augment the system, and so he very easily was able to edit this with I'm not going to say basic MATLAB knowledge, but he can change the front end, can change the back end, and so with all the systems in the lab, we have about 8 different systems, and to be fair, each one is tweaked slightly, but then we have a core version. That is the one that we're disseminating, and then we're providing updates to. So it's all just done with one very simple DAC board here. This looks like a complicated diagram, but it's very simple. One thing I will note, though, because we work primarily in neuroscience, there's a whole other world of actually having stimulus for your fish and your flies, and as Paul mentioned, we have cameras watching the samples. So all of that as well, we've found pretty easy to integrate using things like Arduinos, and we have some code in the lab that is Python talking to MATLAB and integrating those things with triggers and so on. But again, part of what we did was we actually made the microscopes simpler so that all these control problems actually were not such big problems, because I'd been through so many problems with that in the past. So after we've done the data acquisition, we have a very simple data viewer here, which allows us to check everything we got, check all the metadata, and then we have this cool pipeline thing here where you can set up all the different things that you want it to do to the data and hit go, and that's been developed firstly by me, then Wenzi, and now Shilpa in the lab. And so it enables all of these different steps of analysis that you want. And then we built our own little image viewer as well, because I got tired of people using ImageJ. And again, this has been a lot of Kripa has kept this going, so it lets you just explore. And this is all just done in MATLAB. I wrote this in an afternoon. And then anybody who wants to can kind of change it and tweak it according to what they're trying to do. And then obviously we can also export our data very easily into formats that can be read by ImageJ. I don't know if you know, but Imaris has a brand new free image viewer, which is just beautiful. You can just load any format of data into this thing and you can spin it around and look at it. You can't save movies, you can't do quantitative analysis, but it's been very helpful for our collaborators, so we can send them data and they can at least start to explore it in 5 dimensions. And that's been very powerful for us. Or my very favorite thing is to load it all into a MATLAB workspace and play with it on the command line and with scripts, which frankly, for the sort of novelty of the things we've been trying to do, between having to track cells over here and do dimensionality reduction over here and denoising over there, it's actually very nice just to have the data right there where you can access it and prototype at least the analysis routines that you want to do. And again, that's been Kripa and Richard. Richard recently just wrote something that ports the whole thing straight into Imaris. And just so you can see it, this is our old spam image software, which is another front end that we did in MATLAB, and a little image viewer, which we found to be, this one's more complex and annoying, I have to say. And that's it. I want to acknowledge my students. So this is my team that I have working on this, and I threw this in here as well because we have another system which is an LED based, and over the summer I hired a master's student here who's been just converting that whole thing into a little Python Arduino based shareable thing. So that's it. Questions? Yeah, go ahead.
Not really, actually. Yeah, I don't have anything to say.
All right. Yeah, hey, my name is George. George Janelia. I work with a company called Vidria Technologies. We are actually a spin-off of the Janelia Farm Research Campus, and our office is actually located just across the roof, just like about 5 minutes walk from here. So we are pretty tightly integrated in the Janelia community, and a lot of microscopes here actually run our software. So we are basically the developer of the software package called ScanImage, which you might be familiar with Sorry about that. ScanImage is a software package to control laser scanning microscopes. It is an open source package, so basically the source code is available. It is, the user interface is all MATLAB based, so you can script it very easily. And we have about 1,500 registered users on our website. So similar to Micromanager, we don't really have a very good way to count the actual installations of ScanImage in the world, but 1,500 registered users is a metric that we can pull from our website. Okay. So ScanImage has a lot of stuff that you can do, right? So we do linear scanning, we do resonance scanning, we control Pockle cells, shutters, we do online analysis. Obviously, we control galvos and resonance scanners, we control stages and cameras. So in some sense, we have similar, similar requirements as Micromanager, and we kind of think, I think we basically come across the same issues in many ways. We also partner with several microscope manufacturers to bring our software onto their microscope. So examples are Scientifica, Southern Instruments, and SOAR Labs, but basically ScanImage really runs on all kind of hardware and microscope, and we mostly serve the DIY market as well. Okay, so now I want to talk a little bit about the challenges that we face in ScanImage, right? So several of the speakers already mentioned that a big part of, to make your microscope work is basically get all these devices that you have synchronized. And the way that we do that is we use an FPGA to basically run an acquisition engine, right? So we don't run it on the acquisition engine itself on the computer. We run it actually on a piece of hardware called an FPGA. An FPGA, basically, you can think about it like an empty chip that has certain resources like logic gates and lookup tables and so on, and you can basically wire these resources together, and that gives you a very deterministic real-time system that basically gives you nanosecond latencies. So that's what we use to generate all our triggers, generate all our sample clocks, and so on. And in the past, what we have done is we have used National Instruments hardware, such as this PXI chassis, and other data acquisition cards. And what we have noticed is that one of the big issues is it's okay to use this stuff if you want to get one microscope or two microscopes working, but we try to run on hundreds of microscopes, right? And everyone basically can use their own combination of data acquisition cards and so on, and all of them have their own little different quirks, and it's very hard for a software developer to support all of these different hardware combinations that are possible when you combine different National Instruments boards. So in 2019, basically, we pulled the plug and said, hey, this is completely unsustainable, right? We had to support so many legacy cards like the 6110 here. I think that was basically introduced in the 90s, right, and still around. And we were like, okay, so we are trying to do our own thing. And there's this quote by Alan Kay that says basically people who are really serious about software should make their own hardware. And we kind of took that seriously. And we implemented our own hardware, which is like one nice, very nice hardware controller for microscopes that includes an FPGA that's on the board that basically allows us to do this tight synchronization of all devices that we control in the microscope, right? It has, what you see here is it has 12 analog inputs at 1 megahertz that is used to control galvos, PMTs, Pockle cells, and so on, right? 12 analog outputs, 12 analog inputs. We have a load of digital inputs and outputs. And then, of course, we have fast analog inputs and for acquiring PMT data. And the key point to this is that we have that all of these outputs and inputs are controlled by the FPGA and are very flexible to use, right? So we have one acquisition engine, and that basically is controlling the entire microscope in hardware. Yeah. Thanks.
Okay, hi everybody. I'm Jeffrey Kuhn. I am now a microscopy core manager at MIT. And so I'm now starting to work, it's been about 7 months, been working with a bunch of disparate instruments, disparate software to control them all. So getting an idea of what's out there in the commercial world for the first time, mostly. In my previous incarnation, we were doing a research project with I'll just tell you a little bit about it rather than show you slides, but it was a scanning polarization microscope. And what we had to do, and we were using Micromanager to control it, but the idea is that you would scan wavelengths back and forth, and that translated to scanning polarization states. And we were trying to do this as fast as possible, you know, take 100 milliseconds to take maybe 10 or 11 images, and have wavelength switching built into that. So I wrote a lot of Micromanager device drivers. I added a lot of modern C++ template-based stuff on top of all of this. One of the things we had to do was outsource some of the device driver management hardware to open source hardware like an Arduino. So we had an Arduino controlling an AOTF because I could get the latency down with something that was an embedded board. So, you know, I've had it, and one of the issues I had with Micromanager was that it didn't, you know, when you're trying to do wavelength scanning, that doesn't fit into the acquisition architecture. So that was one of the main issues that I had to get around, was the lack of fitting into the type of device driver manager Micromanager was dealing with. And another big issue we were dealing with was passing information straight through the GPU and doing all the calculations on the fly and spitting out both the raw images and the, let's say, processed polarization state images as fast as possible, and trying to do that from the Java side, which was a little bit of a difficult thing. So just to talk about some of the, over the course of this project, I got a lot of, you know, things that I loved, and I've always loved Micromanager. I wrote my own ImageJ-based acquisition software in the 90s, and so when Micromanager came about, I was like, oh, this is glorious. Someone else is doing this. I don't have to do it anymore. It's got really simple GUIs. It's very easy to write GUIs in Micromanager and to do custom controls and to set up states for your microscope. In the Java side, some of the dislikes of, you know, what I don't like about Micromanager is there are multiple layers between gathering an image and displaying it and processing it, and getting it and figuring out the path that Micromanager takes and feeding it into that is very difficult. It's set for, as you know, the acquisition engine is set for, you know, channel, Z, and position, and if you try to go away from that model, it's rather difficult to fit into it. And the drivers, as I said, there were places where it wasn't abstract enough. It was very difficult to put drivers on an Arduino, for example. But just to, I don't want to go too much into, you know, like no array types and the hash table based properties. Can be kind of slow at times. But one of the things that I keep hearing is that people are using Labview, and Labview is, you know, it's difficult for people to run microscopes off of Labview. But there are a lot of other experiments that people are using Labview for, and they're all sharing the same frustration of driving and timing that Labview users throughout the world are using. And here we've got an open source platform for timing and device, and a lot of people that have a lot of good knowledge in using microscopes and doing all this high-speed timing. But opening it up to more than just microscopes might be a good model for getting more people involved in this effort, right? So that was just one of my observations from all of this. And the other thing is that the open source hardware revolution has really taken off, and getting your devices, everything's written in C++. Having everything written, being able to compile your device drivers for the Arduino, for example, and talking to them back and forth might be a good thing to think about. Anyway, all right. Thank you very much. Next person. Here we go. Thank you very much.
Don't worry, I'm not going to plug in. It's just I have terrible memory, so I wrote stuff down on this. Hey, so I'm Sunil Kumar, and I'm from Paul French's lab, who spoke earlier. And basically, I do some software development, but I don't come from that sort of background. I've mostly started off in Labview and have now gone on to using more micromanagery stuff and a little bit of Python. And part of the reason that we're doing this kind of, or have done in the past, this kind of transition is to make stuff well, more openly available, stop having to pay for Labview licenses, amongst other things, and then be able to just give it to people and say, yeah, you can have it, you know, everything's free, just download the software, it'll work, no restrictions, and so forth. So having said that open everything is great, I will now commence with the airing of grievances. But one of the things that kind of gets a little bit problematic with Micromanager at the moment for us is that we like to do weird stuff, so like fluorescence lifetime acquisitions, and we would like to sort of merge doing that with other modalities. And the basic assumption in Micromanager is kind of that what you want to do is set something in some way and then take some number of images, and sometimes you want to mix up what you're doing, do things like rotate stuff or change delay lines and things like that, which aren't kind of in the normal sort of channel model. And in general, support for weird data shapes, say not the same number of lengths in each dimension of different steps of an acquisition is kind of a difficult thing to work out. One other thing that kind of would be nice is to have almost like more than one acquisition engine running at the same time, so that when one's doing its slow time sequence, the other one can just jump in and go off and do other things, and then switch back to the other one when it comes time to do next sequence of acquisitions. Getting metadata reliably recorded and, let's say, set up in the first place has been sometimes painful. Trying to work out how to actually get other software and other programs to interface with Micromanager has been an issue, including, let's say, grabbing camera images for an autofocus instead of getting images for the main camera, because some assumptions that were made. Again, we still love it, just these are things that we would love to do. Outside of that, something that's sort of just generic is that almost everything has mediocre instructions for usage or good instructions for usage of this bit of software. Instructions for development are like almost non-existent in comparison. So we often sort of end up relying on just going off to, you know, let's say Stack Exchange, or just Googling stuff and saying, oh, this is probably a reasonable way to do it. Let's cut and paste that and just fix it. And as for best practices, I'm fairly sure that's not on there, but you know. Other bits for kind of useful would be to have everything a bit more modular, maybe. So you can start inserting stuff in between bits of the pipelines that bit of software would go through, just to have the ability to intercept stuff, say to apply compression, or even do localization or something in the middle. That's pretty much most of the grievances done. Oh, and just communication with other software, even from outside of the domain. Like presumably, if we go into a more automated future and like stuff like, say, sample handling will be more automated, and if you can just get something to do the whole experiment for you, even better. Last bit, UI stuff. Micromanager is quite nice for doing UI stuff. In, say, Java, it's not so bad to do things. Python is a bit of a pain to try and make a UI. Having a friendly UI, or the ability to put a friendly UI on top of stuff, is what takes up a little bit of my time at the moment. And just having people use it having people use some software in the first place is a matter of just them being happy enough to use it in the first place. Last thing on my wish list thing, basically, you can do things like macro recording in ImageJ for processing. Why can't we do that for acquisition? Just go through these steps, set it up, record that, and then just do it automatically. That's me done.
Do you have HDMI cable here? Which one is it? Oh, okay. Enough. Right. Okay. So I'm Chusong Li from Harry Schraff's lab in HHMI and I'm a postdoc here for more than 1 year. But today, I mainly talk about what I have done in my PhD period in Hong Kong University of Science and Technology. So basically, several years ago, I wrote my own control software using the so-called C#.NET. So it's quite different from C or Labview or MATLAB, but it's more like Java and Python. Right, as you can see that on the image window in the scanner control, shutter control, and also you can select the objective for different applications. And also includes the piezo control and also stage scan, XYZ scan. So after that, because we have several lab members during that time, and they also asked me the question, so how your code works. So I just puzzled about why they always ask me the question. Just wrote the documents here. So just look at the PCIe basics so you can understand my code. And of course, 1 year later, we decided to start stimulated Raman scattering microscopy. And you need to synchronize your microscope and also your software with APE, laser, and OPO. So I wrote this part and linked the OPO control with our software. And also we can add the Serlabs components into our software. So I think that's the best part of the C#.NET because I think the first one is GUI programming is very important. As far as I know, the best GUI programming in the world is still Labview for our usage, right? But WinForm in C#.NET can also support that. So it's very easy to use and implement. So it can be comparable to Labview to some extent. And second one is that I think most people in undergraduate periods, the first language they learn is still C, right, or C++. So the C#.NET, I think the programming style is very similar to C, and also in Java and Python. It's the object-oriented properties makes you easy to learn and implement, right? And also I think that if you don't understand anything about C#, just read the MSDN document. It's very easy to learn. And Microsoft itself supports almost all the DLL and API supported by other companies. Whatever you need, for example, PCO or Hamamatsu or Photometric, right? They all support the DLL. But I don't like C# is that it's still very tedious to write the C-like code. If you want to open a camera, in Python only need one statement, but in C, you need maybe more than 10 statements. That's why I don't like it. Okay, So the program and the code I'm using now is not based on C. It's actually written by Dr. Andy, right, which was also our lab mate in Harry Schraub's lab. And while the GUI is very clean and clear, and I like it, but so the reason why we use Python, I think, is that life is short. Do not waste your time on coding. Experiments is more important than coding itself. So learn some Python, especially deep learning and machine learning today is so hot, right? And it's also powerful and easy to use a library. For example, you can use NumPy to do the matrix manipulation and the computing, and also you can use just import the piglet for your display and the camera control. Of course, I think there are, based on my understanding, there are also some disadvantages of Python I don't like. The first one is currently we are using Python 2.7 in our lab, but now this software is not supported anymore. So, right. And also, I think we rely on too much on the external libraries. It will make me feel that I lost the control of the software I'm writing. That's what I don't like it. Okay, here's my talk and my perspective about the C#, .NET, and the Python. Any question?
Is Anthony Leonardo here? I missed him? No, right? Okay, then please, yeah, sorry. Brian.
You were very kind. I was prepared for more criticism.
I also don't have slides, but just the laptop as notepad. So I'm Brian Long. I'm a scientist at the Allen Institute for Brain Science. I am working on a project that is sort of from the scientific perspective. The goal is to map different types of neurons in the brain at the scale of sort of maybe a whole mouse brain-ish. The approach is to use transcriptomics, so image-based transcriptomics, which is using microscopy to quantify how much mRNA is in tissue. So we have thin sections that we start with, and we're using bar-coded readout methods and sort of Murfish-style chemistry. On the microscopy side, what this ends up looking like is a multi-channel sort of multi-round Z-stack in epifluorescence. So this is not fancy in the terms of microscopy, and really more of what my work is trying to get a system that has been kind of described at the kind of nature methods level into something that works in a pipeline environment where we have multiple rigs deployed and they're running all the same software and they have a high uptime and that things don't break. So that's a little bit different than the kind of tinkering development use case for Micromanager or for sort of microscopy software development. But it does kind of force you to deal with some of these user-facing issues about like what is it like to run the microscope, how easy is it. Deployment becomes something that you actually have to care about instead of it just working on that one rig that's attached to that one piece of equipment. So the software that I'm using right now is a module that I wrote inside ACQ4, and so I'm going to take 10 seconds to plug for ACQ4, which is a Python-based acquisition system that Luke Campagnola wrote over the last sort of 10 years. That is a framework to do different kinds of data acquisition, primarily around electrophysiology, but it works reasonably well for microscopy as well, and it's an easy place to put stuff if you're coordinating a bunch of different activities across different devices. So we're not talking about fast timing, but we're talking about different kinds of chemistry that happens in different rounds, different labeling things that happen, different imaging things that happen over a large scale over 24 hours or more while no one's there. So it's a platform that works reasonably well to do that. We do use Micromanager under the hood mostly for the sake of the drivers. And that's the second plug that I'm going to make. That is another project that Luke has started, very sort of early days on this, but the idea is to try to aggregate Python drivers to avoid the copy-paste from GitHub thing that we've already heard about. Come talk to me if you want to hear kind of more about that. Some of us are in the room are already kind of trying to at least plan out what that might look like. And there's actually a lot of overlap in the discussions there with the discussions around Micromanager for the purposes of making stuff usable for other things. So, you know, we all know, I mean, if you've ever written a driver for Micromanager, there's this version bumping problem that is something that would be fun to talk about while we're here, to try to see if there's a way around that for the future, either for whatever is going to happen for Micromanager or for other projects. So how do you upgrade or add something to a driver that's part of a group that then doesn't break functionality across other devices? So now I'm way off in the weeds, but it's certainly something that I'd like to chat with people about. Downside of ACQ4, just like we heard, Python 2 versus Python 3, the conversion is a work in progress, but I think it's going to be, it'll be doable. And then having Micromanager as a dependency inside a bigger project, there are some kind of configuration issues about who kind of owns a configuration and who parses a configuration file and who gets to decide, you know, where, you know, who owns what, how you characterize a device that's loaded into your whole system. And that's something that, for me, building something that's a large system, many components, but needs to be deployed, you know, 5 or 6 times and run all the time, it's important for me to be able to say, like, exactly where the configuration lies. So that's all I have, and that's my time. So thanks.
Okay, Rusty is going to be the last talk before a short coffee break.
Hi, I'm Rusty. I manage the imaging department for the Allen Institute for Brain Science, which means all of the ex vivo light microscopy goes through my lab one way or the other. And the biggest thing that sets us apart from an academic lab is scale. We don't do that many things, we just do a lot of them, and this is on the order of several thousand specimens a year. And you can kind of do some quick arithmetic to understand, you know, if your microscope has a problem where 1% of the time it shuts down or drives the objective into the stage, then, well, if you were doing 10 specimens to get your Nature Methods paper out, then that's not really big of a deal. But if you're doing 5,000 specimens a week, that's going to happen, or 5,000 specimens a year, that's going to happen once a week. And so one of the driving factors for us is repeatability and reliability. Again, we don't do that many different modalities, but when we do them a lot. So let's say, for example, we do quite a bit of just bright field slide scanning, and we have 8 instruments that do that. We have serial sectioning 2-photon systems that we run, and we have 6, and we run 1,200 brains a year. And so being able to have reliable throughput and being able to have very high uptime and have systems that when they fail gracefully, that becomes incredibly important and becomes a challenge in integrating any new systems that we may use. On top of that, keeping track of metadata about the specimens and integrating that metadata into our larger database actually takes more time and effort than building the microscope itself. And so that means that if it drives on Micromanager, which we very much prefer, or Python, or if you really, really twist our arm, Labview, then it still needs another layer on top of it to be able to collect, at the very least, be able to scan a barcode on a slide so that you can enter what specimen that is, because simply writing it down in a lab notebook absolutely does not scale. And then if you look at like the project that Brian is leading, that includes information about chemistry and lot numbers and reagents and all of that other stuff that most graduate students like to just sort of sweep under the rug or write down on a piece of paper somewhere, that we need entered in a database that's going to be recorded and kept, eventually released to the public in a decade. And so this, like I said, it's a unique challenge in a software environment to be able to put that in, and integrating with what's essentially a legacy database becomes a giant challenge. That said, the thing that, the reason we come back to Micromanager as often as we do is because it's kind of this devil we know problem. We know we can get something up and running. We know we can get a new instrument up and going, especially with the driver support that's there. But then the challenge is this upper level integration that Brian hinted at, where you have Micromanager is integrated into another product that maybe that is controlling the acquisition, but you also have this other communication with things in the building and other systems that you need to control. And so, yep, I'm standing between you and the coffee break. So I just say that's kind of from my point of view, that's the interest I have, is being able to integrate whatever system we decide is the future, being able to integrate that into a larger ecosystem that lives not just beyond our lab, but into essentially an enterprise system that allows us to do the scale of science that the Allen Institute needs to do. So, thanks.
Okay, thanks a lot to all the speakers of the first session. We're going to have a coffee break now for 15 minutes, and then we're going to continue with the remaining speakers. Thanks so much.